I'm a senior field applications engineer working in the military space for a company called Abaco Systems, and today we're going to talk a little bit about deploying AI in defence applications. That's quite a broad topic of conversation, so I'm going to be a little bit specific about what we're going to cover this afternoon. So, AI has already been deployed in a lot of application spaces within defence. The Pentagon uses a lot of data center, GPUs, they're used a lot in GCHQ. This talk is going to focus on deployment of GPU and AI technology within the defence space. I'll just hold on and let you late arrivers. Hello? So this presentation is going to talk about deployable AI. So that really talks about three verticals. That's naval, army, and avionics, so military, air force. So we're going to be talking about the challenges involved and what the requirements are within the military to get AI at the edge. And we're really going to be focusing on inference more than training. So training is, we've heard a lot about training this morning, about how to train your data, how to collect data. Training is a specific problem within the military space because the data that you're training against is almost certainly going to be classified. So a lot of training that happens within military applications is happening in the private cloud, and that's an interesting challenge for our customers because they're not used to working with high-performance clusters to do training, so they haven't put all that infrastructure into place. We're not going to cover the challenges involved in training for military applications, although it is something that needs to be considered. We're going to focus on the deployment of those trained databases, those trained networks within the battlefield. So with that in mind, let's move on and talk about what I do and what our company specialises in and why we're really focused. So we're a military manufacturer of hardened technologies, so we produce FPGAs, GPUs and CPUs that can perform inference in harsh environments. We're a global company, we manufacture around the globe, and we've got a lot of capability, but a lot of the stuff that we do is manufacturing of NVIDIA GPUs, AMD and Intel CPUs at our headquarters in Toaster and in Huntsville, Alabama. 50% of the global defence spend is in the US. So as you can imagine, most of what we do is aligning to US programs and US Department of Defence budgets. But we also have a lot going on in Europe as well. This presentation is going to focus on what's going on in the UK and what's going on throughout Europe and NATO countries. So we will talk specifically about certain programs and try and delve a little bit deeper into those. So the first major challenge that you're going to have when you're trying to deploy your application into a defence application is going to be primarily environmental. The requirements for things that fly have certain qualifications, so if you're working in fighter jets or commercial airliners, then there are certain standards that you need to qualify against. So there are GPUs flying around today in drone applications, Predators, Reapers. There are DARPA-funded programs that have GPU clusters within them. And again, although they are not safety critical, they do have hardware requirements that we need to adhere to. In avionics, the requirement that you will need to adhere against is a requirement called DO-160, and there are testing within that for rapid decompression there and to deal with temperature fluctuations and pressure fluctuations when operating at high altitudes. In ground applications, you'll have to work to a different standard called MIL standard 810G. So your GPUs and your FPGAs will not have to meet these requirements. They have much higher shock and vibration requirements. So as you can imagine, if you've got technology driving around in tracked vehicles, that's quite a harsh environment. That vehicle may have been may have been sat in a desert, maybe at 50 degrees and has to start at extreme temperatures, or could be somewhere that's freezing cold in the Arctic and maybe needs to start at -40. So extreme temperature ranges, high shock and vibration, these are some of the environmental challenges that you have deploying GPU applications. I'm going to focus the majority of this talk on ground applications. So in naval, it tends to be more like a floating data center. So if you see a big naval frigate type 45, for example, there's a lot of space in the bowels of that ship, and it looks pretty much like a data center. And they actually go and buy most of their GPUs from HP and Dell, and it's more of an enterprise environment. It's a little bit different on the deck. if you've got a GPU-enabled tracking system, doing some kind of AI to do object localization, object identification, that's an interesting corner case for naval applications. And again, you're going to have to meet high levels of ruggedization for salt, fog, humidity, so you're exposed to the elements when you're on the deck of a ship. So we are going to see the use of GPUs for object classification, object tracking on naval type of trackers. In the air, you're going to see a lot of GPUs being used in situational awareness, so cameras looking at the ground, monitoring certain areas, looking at hyperspectral imagery to look for ground disturbance, for IEDs. There's all sorts of applications, drone applications, which will track humans, vehicles and things within a certain battle space. This talk today we're going to primarily focus on ground application because that's where the most interesting things are happening today. So we've got a diagram up here of a tracked vehicle. This is a tank. And back in the good old days, it used to be that the military programs used to innovate with technology. So back in the 1980s, the MOD and the DoD had very deep pockets, and they were creating the technology that went into the commercial space. That's no longer true. It's the commercial technologies that are coming from the companies like NVIDIA and companies like Intel that are really moving into the military space. The military is no longer innovating and creating new technology. They are consuming technology coming from primarily the enterprise market. So they're having to adapt and change, and that's certainly the case today. So a lot of the standards that we see today are really around taking those enterprise technologies, InfiniBand, high-speed fabrics, GPUs, and putting those into deployable, rugged, hardened applications. So all of these systems used to be disparate systems. If you take a vehicle maybe only 10 years ago, you'd find that the sighting system wasn't connected to the situational awareness system, the driver couldn't access the infrared cameras, everything was a separate system. Today, things have changed quite a bit. There's now networking on these vehicles, there's open standards, driving fully digitized architecture, so in the maybe going back not even 5-10 years ago, a lot of the camera systems used to be analog, so they're point-to-point connections. They'd only be connected to a single person within the vehicle. A vehicle such as this will have typically a crew of 3. In the turret you would have a gunner, at the front of the vehicle you would have a driver, and in the back you'll have a commander. So there are multiple consumers of the data and the information within these systems, and there are multiple digital systems within the vehicle. So connected to the network, we have systems such as telemetry and HUMS, health and usage monitoring systems. So this is the system that records all the information about the vehicle, engine noise, temperature sensors. So there's a lot of information flying around this network. We've got sighting systems, 360-degree vision systems. We have infrared cameras, visible light cameras, firewalls, routers. So these are very complex systems, and there's a lot of information on there. Today, this information is only available to the commander when they're looking at it. Some of it may be recorded for future analysis, and they're not really doing anything overly intelligent with this information. It's basically available to the crew in real time, and again, it's humans making a lot of those decisions. We've had some success recently with putting GPUs onto military vehicles. Those GPUs were being used to drive the displays, but what we're seeing now is the information on the network is being stored, it's being compressed and recorded, the metadata is all being collected in a central location, and it's ripe for being harvested. So those GPUs that are compressing the data can also do AI, they can do inference on the cameras. So we're going to talk a little bit about how the standards allow for technology insertion and how we can exploit that on these platforms. The interesting thing about military vehicles is they tend to go into service for a long time. In the UK, we've got the Challenger 2 tank, that went into service in 1990. There are new technologies going into that platform today to upgrade capabilities. So to do that on something like Challenger, they've had to rip out an awful lot of the analog infrastructure, and they've had to put in a whole new set of architecture. That's very, very expensive, and that's not the way the government wants to continue to upgrade these programs. So today, they're trying to increase interoperability, and they're introducing open standards and open architectures. The open architecture that we're most interested in, and the one that the MOD use in the UK, is something called the generic vehicle architecture. That's a DEFSTAN 2313. That talks about physical interfaces, hardware interfaces, and software. And the key to this is it talks about software for future technology insertion, interoperability, reduced cost of ownership. Software is a very important part of the standard. In the US, you'll see something called the Victory Standard, which is very similar. It also talks about fully digital architectures, and when you look at both of those very closely, when we talk about digital architectures, we're talking about Ethernet networking. Ethernet with a 10 gig backbone, so that you can just add in a box onto the Ethernet switch, and you can start doing things with video, audio, and telemetry data streams very, very quickly. So these open architectures are designed to scale. So the technology that you have on a quad bike or in a Land Rover can go into a 4x4, can go into a military tank. So it's about being able to develop once and deploy multiple times on multiple platforms. So the software that you create for your main battle tank will also work on your quad bike, maybe on a lower power processor. So things like you may only have a very low powered CPU on the 4x4, but on the tank you might have a GPU, you might have some FPGA resource, so you can increase the capability of your AI. And it's scalable across all of those platforms. So software scalability is very important, as well as hardware scalability, being able to take something that will physically fit and mechanically will work with the same power supplies, the same types of connector. And again, it's all about, for the government, it's about reducing the cost of ownership and increasing competition and reducing through-life costs. And ultimately, with new vehicles, the vehicle that we deploy today will be in service for 30 or 40 years. In 10 years from now, we may have a whole new capability with AI that we want to insert into this platform, and without having to rip out the cameras and rip out, tens of thousands of pounds worth of equipment, we can insert that capability onto the vehicle by rapidly deploying a processor box that has a certain capability, connecting it to the Ethernet backbone within that vehicle, and deploying new capabilities very quickly and very cheaply. So that's great news for people that are developing new and interesting technologies that can increase survivability, help achieve mission objectives. So that's great news for us, and that's great news for people working in this industry. So the UK government has something called the Land Open Systems Architecture, and it is truly open. Anybody can go to the MOD website and they can download these standards. You register your email address on the LOSA website, and you can get all of this information about how a display needs to look, what connectors are required within a processing unit, what protocols you need to use for audio, what protocols you need to use for video, how do command and control messages go around the vehicle, and what do those look like. So the Land Open System Architecture is an overriding strategy that drives interoperability and standardization within three key areas. The first area is the generic vehicle architecture. So this is a vehicle architecture, and again, you can think tanks, 4x4s, things like that, quad bikes. It covers everything, anything that's moving and within the battle space. The second part is the generic base architecture. So as you can imagine, a base will have a network, it will have a security system, it needs to be secured, RF communications, cyber security. So it covers all aspects of the base security. And then finally, you have the soldier architecture. Soldiers are mobile, they may have a backpack computer with some capability, some level of AI. There might be wearables, touchscreens on the arm. So that covers the standardization for the soldier. Now, within the vehicle architecture, I'm going to focus in on the vehicle architecture because that's the most interesting and that has some decent volumes behind it. We'll talk about some of the programs. That has something called the VIVOE standard, the Electronics Infrastructure for Video over Ethernet. Now, this is great news for anybody doing video because what it means is the video is not going to be some bizarre standard that you've never seen before. There's a lot of proliferation in video standards. The automotive industry tends to use coaxial, cheap cameras, GSML type cameras. Broadcast industry uses their own standards. So every industry seems to have a different standard. We're seeing the deprecation of the old legacy standards, so you're no longer going to see kind of PAL and NTSC video streams. But the VIVOE standard is great news for people looking at inserting technology into these types of architectures because it's all Ethernet streaming. And the Ethernet streaming is not particularly onerous. It's using something called real-time protocol. So if you have a vision system or an algorithm that it can go and detect anomalies or can look for artifacts within those video streams on those platforms, you can simply plug that into the Ethernet infrastructure, and thanks to multicast within the Ethernet specification, you can subscribe to the channels and the camera streams that you want, and you can start consuming that video in parallel to the driver and the commander and the gunner. So that's great news for anybody looking at technology insertion. So this is something that we developed. It's a digital rugged video recorder. This has GPUs in it doing AI and compression. So an important thing is to be able to record the things that you saw while you're driving as well as the commander being able to make to be able to make decisions to achieve mission objectives in real time, also being able to archive that data and tag the information with the appropriate tags. So if you see a vehicle, you may tag that video stream with the registration information. If you are counting the number of people around the vehicle, you can tag the video with the number of people that you saw and the types of objects and things that you saw as you drove around. So having GPUs within the vehicle means we can do this very quickly in real time, and then that information, after the mission is complete, can be taken away and placed in a data center for mining later on. So what the MOD and the DOD want to be able to do is to say, if there was an incident today where a gun was fired or there was something happened in a remote town, they could then go and mine that information and say, were there any other vehicles within a mile radius of this? Was there a vehicle within a mile radius of this any time within the last 12, 15, 18 months? And get the information, the video streams, the audio streams from those vehicles, and be able to analyse that very, very quickly to try and find information that might be pertinent to the incident that just occurred. So, and again, that doesn't necessarily have to be all ground vehicles. It could be drone applications within the area and different types of vehicles. So again, that information is extremely valuable, and it's not only used in real time, it's also archived and then stored and used for missions at some point in the future. So let's talk about the size of the opportunity here. So I'm only going to talk about some of the larger programs, but there's an awful lot going on within the defence space at the moment. The recorder that I just showed you is part of the UK Ajax program. That's over 500 vehicles in 4 different variants. There's a bridge builder, a turreted version, there's an ambulance version, and all of those have GPUs inside driving the commander's display and AI in there doing various things on the vehicle. So that's one of the world's first fully digital platforms designed to the GBA specification for the UK MOD. I also mentioned Challenger 2. This vehicle's been in service since 1990. That's being upgraded and new capabilities are being added into that platform. Probably the most sophisticated part of a vehicle such as Challenger is in the turret. Electronic countermeasures, sighting systems are all accelerated with GPUs. Those algorithms are process intensive and need to be calculated extremely quickly to make firing decisions. So there's a use for accelerated processing specifically in the turret, and both of these vehicles will have GPUs in the turret fulfilling those roles, as well as GPUs within the base of the vehicle, archiving information, compressing information, indexing, adding metadata onto those data streams. There's a lot of money being spent by Australia as well. So this is a Boxer vehicle. The Boxer is a Rheinmetall vehicle, and again, it seems to be taking off. It's been around for a while, but now there's some major programs just been announced. Australia buying 211 of these platforms. I think down here this is a non-turreted version, so the military infantry vehicle version of that is a directed purchase from the MOD. They're going to be buying 508 of those vehicles, and they're not going to run a competition for that. We don't really know what the capability is going to be of the MIV variant, but there's certainly going to be a lot of capabilities that's going to be sought by the UK MOD, and that's something you should be registering your interest in now if you think you've got anything to offer on those platforms. Phase 4 of the Land 400 program, which is an Australian program, is going to be 450 new fighting vehicles. Those vehicles are going to have all new capabilities. Again, that's out for tender at the moment. That's looking like that could go to Rheinmetall, General Dynamics or BAE Systems. It's a bit of a 3-horse race. In Germany, we've got the Lynx, which was announced at Eurosatory. This is a brand new Current generation battle tank, again, nobody has deployed this yet. It's a completely new platform for Rheinmetall. They're offering that to the Australians, and interestingly, this is also being offered to the US military in conjunction with Raytheon for a replacement to the Bradley fighting vehicle. And then in the UK, we've got the Warrior program, which is a much smaller tank, and then if we look in the Middle East, they've just ordered 490 new vehicles from Nexter, the VBCI platform. So the numbers aren't massive, but the margins are quite high. The cost per unit of a deployable rugged system is quite high, so it's not kind of enterprise grade, it's not going to scale and scale and scale like a software solution. There are limits to how much of this is needed out in there, but the capabilities that they require mean that the systems that go onto these are quite expensive, and they are very high end. So I did put a slide in here about video standards, just because there's so much of a proliferation of video standards. The one that we've talked about first is RTP. Almost every vehicle that you're going to come across, a ground vehicle that you come across, is going to be using RTP. There is an exception to that, is GSML. So GSML is the automotive standard. So pretty much all autonomous vehicles have these GSML coaxial cameras. They operate over a relatively short distance of up to 15 meters, but in a car or a truck, that's not too much of a problem. GSML is being used in something called autonomous resupply, and we'll talk a little bit more about autonomous resupply, because that's another sweet spot where the government is investing at the moment, and resupply is a major problem for armies all around the world. It's a very dangerous area to be working in. They want to take humans out of the resupply and the supply chain. So we'll talk a little bit more about that. All of the other protocols really don't meet the requirements. They don't meet the requirement for multicast and cable length, as well as the high throughput. So kind of Gigi Vision cameras and RTP is really where it's at. And this is what a typical architecture looks like. I'll put something in there. RTP is how the video is streamed from the cameras. It tends to be raw because video streaming is inherently latent, especially when you're compressing. So if you're doing H.264 or JPEG 2000, you find you're going to lose a couple of frames, and that's not really acceptable. So a lot of this video streaming is high bandwidth. That's great because you're not going to have many compression artifacts. You're getting very high quality video at a very high speed. And then you've got a control protocol called Distributed Data Service. DDS is mandated within the IoT. It's a publisher-subscribe model. What it means is your command and control mechanism is coming from IoT. It's very scalable, again, and it all runs over Ethernet. So that's how you will see NATO architectures will be similar to this. GVA, NATO includes Europe, obviously, South Korea, Australia is working to the NATO specification, as well as countries like Japan are all subscribed to the NATO standard. And then on the other side of the Atlantic, we've got the Victory. So, so this is the standard that you need to be looking at for NATO countries and for the UK. I've got a copy of this if you're interested. This is the standard that tells you how to stream and consume video for GBA. We talked about RAW. It allows JPEG 2000 and H.264 are also permitted within that standard. Gigi Vision cameras are allowed within the US, and again, those streaming protocols were considered by the GBA specification, but there is some licensing applied to the royalties involved in licensing the Gigi Vision standard. They work great with vision processing systems. They're very well adopted. It's a driverless model, so Gigi Vision cameras do not require a device driver. So if you've got something that is Gigi Vision compliant, you can buy a camera from anybody and it's guaranteed to work. So that's the nice thing with Gigi Vision. When you've got USB cameras, the problem is you have to have, somebody has to add the video for Linux support, or they have to develop a driver for it, and you get a separate disk, and it's a complete pain in the ass. Gigi Vision is supposed to be a driverless model, so you can buy a camera from anybody. If your application is Gigi Vision, you're good to go. So it's very nice, it's easy to use, it increases interoperability, and again, you're going to see that more on the US and the Victory standard, but also NATO allow for Gigi Vision as well, so NATO countries also use Gigi Vision. There's a little bit on colour space. The reason I put this slide in here is because of the bandwidth requirements. Depending on how you encode raw video, it's going to increase your bandwidth. And I've done a few calculations here. I'm just going to skip over this because I want to get to the bit on deep learning. So Bayer encoding is what's typical in Gigi Vision. You can see as you creep up the resolutions, the bandwidth goes up quite dramatically. And bandwidth is important because most of what you're going to see in a military vehicle is going to be gigabit Ethernet. So as soon as you get up to beyond 1080p with Bayer 8, as you go up to 2K video, you're 243 megabytes per second of bandwidth. You're beyond the limit of a Gigi Vision stream. If you're using YUV, which is typical for the GBA standard, you'll notice when you're up at 1920 by 1080, you're at the limit of a single stream over Gigi Vision. That's why it's important to maybe consider aggregating cameras. If you've got a lot of cameras in your vision system and you want to start doing AI, stitching those cameras together, doing pedestrian detection, face detection and things like that, you're going to need to get all of that video into one place. So that's why bandwidth needs to be considered when you're architecting your system. So the way that we can aggregate is maybe through an Ethernet switch with lots of gigabit Ethernet port. This switch here has two lots of 12 fiber interfaces here, and then it has this is copper interface, so 24 ports of copper, but then 4 ports of fiber optic 10 gig here. So you can take lots and lots of Gigi Vision cameras, you can aggregate all of those onto fiber optics, and then you can use something like this, which is a packaged GPU system on module. So I'm sure most of you here will be familiar with NVIDIA system on module. It's a GPU and ARM architecture designed for embedded applications. So it's designed to be low power, small, swap optimized, and it's perfect for applications such as this, where you are size and power constrained, but you want to introduce additional capabilities around AI and deep learning. So being able to aggregate all of that information through maybe an Ethernet switch, whereas maybe you couldn't take it directly into your accelerated platform, that aggregating it maybe on a 10 gig fiber link is something that would allow you then to start building your vision system. So it's important to understand the requirements of the end user. Do they need to be consuming that video in real time, or can I compress it first and then squeeze those cameras down maybe a gigabit link? So it's all going to come down to the types of things that you're doing. If you need to be doing them in real time, you're probably going to need to be doing them raw, in which case you're going to have to address the bandwidth issue. And again, it's close to the display where we're probably going to be wanting to do all of this AI and this deep learning. And then finally, the other benefit of these AI processors, they're coming from the GPU markets. They tend to have very good ISPs, image signal processing, so you'll be able to correct for barrel distortion using those ISP engines. And the final thing they have is compression engines. So if you've got a link coming off the vehicle, a radio frequency gateway is probably going to be bandwidth limited, then you're going to have to squeeze all that video down. So being able to use those media processors on those embedded devices is also very important. So just a little bit of information for those wanting to get started with vision processing on AI applications. There's a lot of support for Gigi Vision cameras in Linux, so I'm talking about specifically embedded Linux systems here. They're not the only system that you're going to come across in ground vehicles, but certainly Linux has the best support for vision. If you've used something called GStreamer, it's a flexible video processing pipeline which allows you to quickly encode and decode video streams and mix multiple sources of video inside your application. So GStreamer is a great way of getting that video into one location so that your application can then start doing the inference on the data set that you need to do to work with. So if you're using Gigi Vision cameras, you're going to need plugins BAD. BAD is something that's not fully tested. Don't be too scared about BAD. This contains the Bayer encoder, so you're going to need that to work with Gigi Vision cameras. There's something called Aravis, which is completely open source, which is an open source implementation of the Gigi Vision stack. So there's some pointers on that side for how to get started with Gigi Vision. If you're using GStreamer and a GVA architecture, your cameras, this is an example of a camera from Ultra. This is an RTP raw video streaming camera. And if you need to consume the video coming off this camera, then you're going to be doing UDP streaming. You're going to need to decode that. And there's an example of a pipeline that can work with a GVA source within a video network. So GStreamer is great for us. It's great for the defence industry, and again, it makes it really easy to start consuming the video sources within these networks and applying the AI. So it's worth mentioning here, I don't know whether anybody's familiar with the Jetson AGX. Has anybody here had a play with the Jetson, the new deep learning platform? So it's worth mentioning because this is a 40-watt device, system on module. It contains 8 ARM cores. It's got 256 GPU cores for AI, but most importantly, it also has tensor cores. So tensor cores are separate from the GPU cores and are designed specifically to offload your AI algorithms. So these are NVIDIA cores. NVIDIA produced this device, and they have something called Tensor RT, which is Tensor Real Time. That is their inference engine, which is highly optimized for the embedded space. So this device can run at, I believe it's got profiles to run at 10 watts and 30 watts. So again, very low power, but extremely high performance. And again, the game changer here is this now has dedicated tensor cores as part of the silicon. It's not using the GPUs to do those, it's part of the silicon. And this is primarily targeted at the automotive market, where they need more performance within autonomous vehicles to get to level 5. It's also going to be a great platform for the defense industry, where they're swap constrained, they're running off batteries, they need that high performance, and again, this is going to allow us to deliver all of that capability that's going to be required. The Vivoe standard needs RTP, so there's a software under Linux that supports the full RTP, JPEG 2000, and the H.264, all hardware offloaded on this platform. So the streaming protocols are all fully supported, and you've got all the tensor capability. So if you've been to those TensorFlow talks earlier on today, you can do all of your TensorFlow stuff out in Google, and then you can run all of that stuff on something like a Jetson, and it's all hardware offloaded for you. So again, if you're using Caffe or Torch, TensorFlow, all of those APIs are designed to work with this hardware, and again, it's all optimized like crazy. This board here, so it's not a cheap board. I've got the pricing on this if you're interested. These modules are going to be about $1,600. So they're not cheap modules, they are very performant modules, so you can go and have a look at those. So what are the applications? So today there are competitions running in the UK and in the US to deliver capabilities in autonomous resupply. So this is, the last mile of resupply. And these are the scenarios that are defined by the MOD. So this is resupplying the front line over the ground and with drone type applications. So this is all about getting munitions, fuel, and supplies to the front line autonomously. So this is an extremely dangerous area. They call it the last mile of resupply, but really it can be up to 25, 30 kilometers to the front line. So be able to get those munitions not only to the autonomous vehicles, when they're needed, but then delivering them to the front line or fully autonomously using these platforms. So there's a couple of images at the top there. The first one that we have is a platform called the Viking. This is being developed in the UK by Myra, who have a test circuit up near Hinkley on the A5. That's their test platform. The program that's being run at the moment is called Autonomous Warrior. So there's money being invested by the UK MOD to investigate what capabilities can be added to these platforms. Its American cousin is the next one. This is the Centaur unmanned vehicles. That's the US equivalent of that platform. There's another one being developed by Kinetic. This one is a platform by a company in Estonia called Mildef, but the autonomy is then added by Kinetic. So some of these are generic kind of remotely operated platforms that are now getting that autonomous capability. And this is the platform where they're using the GSML cameras. So those are ubiquitous cameras, they're cheap. These platforms are going to ship in volume, so keeping the price down. There are going to be lots of these things driving around if they ever go into production. So again, cost is sensitive on these platforms, and they're delivering standard payloads across various differences. So a lot of these platforms you'll find it can operate off of fully electric or hybrid drive systems. So again, depending on the distance that you need to resupply over, there's various different ways of propelling these. And then the last one, which was pretty interesting, I had to stick it in, was the Black Knight Transformer. This is actually a flying truck. There's actually a man sat in a cab. at the front of this thing, so the idea is they can drive it up to the front line and then just fly the last mile, or it can take off. The Black Knight Transformer is very interesting, and you can see videos of that thing flying on YouTube if you're interested. So those are the platforms where AI is going to be most effective in the short term. So this is the thing that fulfills a government requirement today. So these are the requirements that the government wants to see going into production very shortly. So it's a multi-phase program. So the first couple of phases of the program are really looking at the platforms themselves. The platforms need to be doing something called SLAM, structure, location and mapping. So they're going to have high definition maps embedded within these systems. This is a GPS-denied environment, so the only information you can guarantee you're going to have access to is the information that is within the platform. You're going to be jammed, you're going to be denied GPS, so you need to be able to navigate with all of the things that we're probably familiar with in our vehicles today. So you're not going to be able to have any external stimulus, you need to be able to deliver the payload to the front line and then return back to where you started. So these are truly autonomous platforms with no form of communication. They just need to be loaded up and off they go. So the first two phases are really looking about how they do the route planning. If the map tells them to go down a road and there's a tree in the road, they need to identify that they need to go around the tree and start looking for alternative routes to get to the front line without any assistance from a human operator. So that's quite a challenge. The third part of the challenge really is then, how do you get the supplies to the front line? So can you look at past resupply scenarios and can you learn about when do we need to get food? The food just doesn't suddenly appear at the front line. It needs to be shipped, it needs to be sent out to the front line. So can you look at the resupply requirements of the front line and how can you get how can you predict, track and plan all of that, all of the logistics that are required for resupply? So there's a lot that can be done in AI to help assist the planning of the logistics and the resupply, as well as then being able to deliver that resupply to the front line where it's required. So what kind of techniques are being used? Well, I think we've got our traditional techniques here. Image recognition is very useful for friend or foe detection, being able to look for enemy within, surrounding the vehicle, to be able to detect friend or foe information. So if you encounter a vehicle, is it a friendly vehicle? Is it, can you classify it in any way? Segmentation is obviously very useful when you're doing structure, location and mapping. If you need to find a route through some kind of obstacles. I think this one's interesting, gesture or pose estimation, gesture detection. Pose estimation is getting a lot of interest at the moment in the MOD, because you can identify not only how many people are around the vehicle or around the base, but are they acting in an anonymous in a way that we don't expect. So there's a lot of difference between sticking your hands up and shaking your fist. So shaking your fist is an angry action, but sticking your hands up is quite a passive action. So can we detect somebody coming to a base trying to surrender, or somebody coming over shaking their fist in a threatening way, and can you alert then the base commander that there's a group amassing outside of the base and they're acting in a way that you might want to be alerted to. So being able to train AI to recognise gestures could be extremely useful in a vehicle and within a base. So I think there's a lot to be done there. And again, it's certainly an interesting area of research. And then we've got some more traditional use cases. It's not just visible light that's available to these camera systems, there's infrared as well. So we can also train the AI to recognise when to fuse infrared light. So if you're working in a degraded environment, maybe at night time, the AI could say, well, let's have a look at the IR. The IR's got a little bit more information, and now we can start blending that into the visible light to increase the fidelity of the image. Quite concerned about whose responsibility it is now to do the training, because they're traditional real-time operating systems people. They're quite low level, they only write C code, they don't really do a lot of training in AI. So there's going to be a lot of work that needs to be done to get those engineers up to speed and thinking more about how do we now create neural networks to solve these problems rather than using traditional techniques. So it's an interesting challenge. A lot of the data is going to have to go on these private clouds, as I said before, because the information that you need for training is inherently going to be secret. So it's going to present quite a big challenge. So looking at some of the other applications that we've got, this was a module that we did. This is a Tegra K1, so this was the first system on module that came out from NVIDIA. We did, this is a Com Express module, this is an industrial form factor, and that was putting some CUDA processing next to this gimbal at the top here in an airborne application to actually do some processing on that vision system. So this is an example of where AI and GPUs are placed very close to the camera interface to do something in real time at the edge of the network. And here are some other use cases. So what do the products look like? There is an open standard for hardware. So in military, these are the kind of form factors that you're going to see. These don't look like computers that you will have seen before, but this over here is a standard called VPX. It's a Vita standard. Vita did the old VME standard. If anybody's come across VME bus, it's a 40-year-old bus architecture. It's pretty slow today. People still use it. Don't ask me why, but they still do. It only goes up to about 320 megabytes per second. These connectors over here can do multiple gigabytes per second, so it's an order of magnitude better than that old technology. The committee that came up with the original standard is called Vita. They produced this standard here, and these boards are designed to do DSP and AI applications at the edge of the network. So this over here is an example of a GPU board that can run AI algorithms in a rugged environment. This is a GPU only, so you need a second board for a host processor, so you've got some high bandwidth PCI Express lanes to connect this to something like a Xeon processor. So maybe you have a Xeon processor with 24 cores over here, and then you've got your high core count GPU in a second slot. This one here is an example of an x86 CPU and a GPU on a single blade. So this is a board that can be plugged into a system to give you a level of AI within a single slot. And then more today, customers are looking for packages that can rapidly deploy onto a vehicle. So if you have an application and you need to do AI in a rugged environment, then we also have these packages to the right that use something called the 38999 connector. This is a standard within military applications. It's a gasketed connection. One of the harshest tests that this needs to survive, other than the drop test, is the hose down test. When they go into a military vehicle and they want to clean it, they go in with a high-powered hose and they hose the whole vehicle down, and the electronics stay inside the vehicle. Nothing comes out. So there's some quite harsh tests that you need to meet to be able to put things like FPGAs, GPUs, and processors inside military vehicles. And then finally, we need to educate. So I talked a little bit about our customers being low-level C API type of customers. They use things like embedded microkernels, QNX, and VxWorks. They're C programmers. So to help those customers get onto the AI bandwagon, they're not familiar with manipulating images using OpenGL or Vulkan, and then doing color space conversion and stitching images together. So to help those customers be able to access the video sources and manipulate those in a way that they need to using their new AI networks, we've come up with a product called ImageFlex, which is a basic C API which allows the customer to manipulate video streams, annotate the information in the way that they need to, whether it be for segmentation or object localization. So they need to start working through those processes to train their networks, and we provide the tool chains to assist those customers. And these can be accelerated on CPUs, GPUs, FPGA. So again, if you've got a low power environment, FPGAs can work very well. GPUs can offer a lot of acceleration. Sometimes the CPU can do what you need to do. But built within this ImageFlex tool chain, we have LiDAR visualization. So if you need to visualize point clouds from your LiDAR, you can visualize that. You can start to stitch the images together to create 360-degree vision systems. We have algorithms that allow you to fuse different areas of the spectrum, infrared and visible light, as well as then being able to test those real-time algorithms out in a development environment, and then squeeze them down onto your target platform and deploy those in your within your program. It's not just vision. We've talked a lot about vision today because that's one of the primary use cases. But we're also using GPUs to accelerate DSP algorithms. So DSP functions is used a lot in sonar, it's used a lot in radar. I've not seen anybody trying to use AI in sonar and radar applications, or those are applications which are prime for parallel processing. Things like anything where you've got a large vector, your vector now is no longer an image in a sonar application, it's now your sonar returns from your sensor array or your radar array. It's just a large vector, and whenever you've got a large vector, then it's ripe for parallelization. So this is an example of signal processing using GPUs to offload. And again, we've had a couple of customers interested in maybe now using some kind of AI to filter those returns. So again, that's an interesting but emerging use case. So we've got a couple of white papers that we've put out. There's a guide to the generic vehicle architecture, which just tells you why do we have the generic vehicle architecture, how does it address technology insertion. It's a fully digital architecture. It's now got quite wide adoption across NATO. It's also being looked at in the US. So again, it's something you should have at least a high level of understanding if you're going to start working in the defence space. And then we've got our white paper just on inference, which is a guide to machine learning and deep learning. So that's it. So that's our presentation. Let's thank you for coming along today. And if you have any questions, certainly come up and have a chat with me, or you can stick your hand up and we can address those out.